So in the previous lectures, we started to discuss about the various experiments which were based on the division of wavefront. So the principle was the division of wavefront. So the first experiment that we discussed was the Young's double slit experiment. So the second method that is dependent upon the same principle of division of wavefront is the experiment which is performed by Fresnel using a biprism. So that is called as Fresnel's biprism experiment. So this biprism, how was this constructed? So it was constructed by cementing base to base two very small angled prisms. So two very small angled prisms were taken and this angle was about 30 minutes. This was a very small angle that was about 20 to 30 minutes. So we know that 60 minutes it make up a 1 degree of the angle. So this small angle was about 30 minutes and these two prisms, they were joined base to base and a large prism angle was obtained and that was about 179 degree. So this is called as the Fresnel's biprism. It was constructed by joining two small angled prisms base to base and a prism was obtained with a very large prism angle of about 179 degrees. So now what is the experimental setup that was used by Fresnel? So this biprism, it had two faces, that is AB face, this tilted portion, that is the AB face, and the second lower face was BA prime face. So a source of light, single source of light S was placed in front of this biprism and light was made to shine upon the two faces of this biprism. So let's consider the light which is falling from the source on the face AB of the biprism. So we know that the light gets refracted and it bends towards the base of the prism. So the light which is coming from the source S and is falling on the face AB, this is shown by blue color, and the light which is falling at the face of BA prime and is getting refracted is shown by pink color. So just to differentiate between the two. So the light which comes from S, this top ray that is shown by blue light, it gets refracted and it reaches point G and falls at this point on the screen. So a screen is kept over here where we observe the interference pattern. So this top ray, it gets refracted and reaches point G, and the second blue ray which is shown over here, it reaches point F, that is it will be refracted towards the base and this will also get refracted. It will bend towards the base and reaches point G, whereas the second ray which is shown, it reaches point F. So this region GF, this whole region GF is covered by the light which comes after refraction from the face AB, and similarly we can see that the light which is falling on the BA prime face, that is the lower face of the prism, it gets refracted and it falls in the region of EH. This pink portion of the region, this is the EH region. So this region is covered by the light that is refracted at the lower face, and this GF region on the screen is covered by the light that gets refracted at the AB face of the biprism. So now when this whole region of light, that is GF region of light, when this is extended in the backward direction, it appears to be, this whole light, it appears to be coming from a single source, that is S1 source, and similarly this whole region of light which is shown by pink color, that is EH region, this cone of light, when this is extended in backward direction, so it appears to be coming from S2. So here we obtain two virtual images of a single source. So here we have obtained two sources from a single source. So obviously S1 and S2, these are the coherent sources and these are obtained by division of wavefront. So this is the one wavefront and this source will emit the another wavefront, and these two wavefronts will interfere with each other. So we can see that the overlapping region is given by this part. This is the region of interference. This whole region that is the region GH. This GH region is the overlapping region, that is here light falls from the surface AB and also it falls that from the surface BA prime. So this is the overlapping region. The light overlaps from the two sources S1 and S2, and this is the region of interference. And in the GH region we get interference pattern. So interference pattern is observed only in the GH region. So here you can also see that we have placed a screen which is also called as stopper. So this is represented by Mn. So this screen or this stopper is used to limit the region of interference. As you can see, the light which comes from this source, if it falls at this point, so it will not be able to travel, it will not be able to fall on the screen. Only the light which falls in this region, it will be able to fall on the screen, and hence this acts as a stopper or this acts as a screen just to restrict the region of interference. This is the distance, this whole distance from the screen, distance between the screen and the source is given by capital D, and the distance between the two virtual sources is given by small d. So you can see that in this experiment the images S1 and S2, these virtual images S1 and S2, they act like the two slits of Young's double slit experiment. So these are similar to the two slits that we saw in the Young's double slit experiment. That is, the light coming from the slit S1, it falls on the region GF, and the light coming from the slit S2, it falls on the region of EH on the screen, and the common region between the two sources is this GH region, and interference pattern is observed on the screen in this part. And this interference pattern, the fringe width of this interference pattern is calculated using an eyepiece. An eyepiece is placed at on the screen. So the work of this eyepiece is to measure the fringe width or the distance between the two fringes. So this you will be seeing in your laboratory experiments, that a traveling microscope is placed so to measure the fringe width or the distance between the two fringes. So this is the whole experimental setup. So we know that this whole experiment is similar to the Young's double slit experiment, where we had two slits, and here also we have two virtual images of the source, and there also we had a screen, and the light from the two sources, it interfered in a particular region. So this whole experimental setup is similar to the Young's double slit experiment. The fringe width, the formula of the fringe width will also be the same as that of the Young's double slit experiment. So in Young's double slit experiment, the fringe width was given by beta. So beta was equal to lambda into capital D upon small d. So lambda was the wavelength of the light which is used, capital D is the distance of the screen from the source, and small d is the distance between the two virtual sources. So we can calculate fringe width the formula of the fringe width will remain the same, because this experiment is similar to the Young's double slit experiment. So the formula for the fringe width will also remain the same. So we know what is lambda, because we know that what kind of source we are using. So lambda is known to us. Capital D can be measured, that is from the source to the screen. So capital D can be easily measured. So what cannot be measured easily is small d, because the S1 and S2, these are the virtual sources, and this distance between the virtual sources we cannot find it directly. So this distance between the two sources S1 and S2 cannot be found directly using a micrometer or using an eyepiece. So next question is, how do we measure the distance between the virtual sources? So one of the methods to find this distance between the virtual sources is the displacement method. The displacement method is used to find the distance between the two virtual sources, that is S1 and S2. So in this method, a convex lens will be used. So you can see in this figure, in these two figures, that we have used a convex lens L1, and over here we have used L2 convex lens. So the other construction, it remains the same, that we have two virtual sources, we have a biprism and we have a screen. The difference is that we have placed a lens at a position L1 between the biprism and the screen. So these sources S1 and S2, the image of these sources S1 and S2 will be made on the screen. So the sources, images of these virtual sources will be made on the screen, and we make this image such that the distance, let's say the distance of the lens from these sources is given by U, and the distance of the lens from the screen is given by V. So the distance of the lens from the sources of light is U, and the distance of these lens from this image is V. So this lens is placed in such a position, first of all it is placed near to the biprism such that a magnified image is obtained on the screen. So this lens is placed at a position L1, and L1 is such that it is close to the biprism, and a magnified image of S1 is obtained. So the magnified image of S1 will be obtained on the screen, and the magnified image of S2 will be obtained on the screen. So this will be S2 prime and this will be S1 prime. Similarly, here will be S2 double prime and S1 double prime. So the image of S1 will be obtained over here, and that will be S1 prime, and image of S2 will be obtained here, and that will be S2 prime. So a magnified image is obtained, and we have placed a micrometer on the screen. So an eyepiece is placed, so we can calculate the distance between the two images easily. So this distance between the two images S1 prime and S2 prime, let's say it is given by D1. So the actual distance between the two sources is D, which we want to calculate. But what we calculate is D1 by using the eyepiece. That is, this is the distance between the two images of these virtual sources using the convex lens, where the distance of this lens from the sources is U, and the distance of this lens from their image is V. So we do a little bit of mathematics over here. Now this triangle S1, this is the source, actual source S, and over here also we have the actual source S. So let's say this is O, and this also is the, or you say this is the O prime, because we have taken the center of the lens as O. This point is O, and let's say this is the O prime. Now we are looking at the triangle S1, S and O. This is the right angle triangle, that is S1, SO, and the triangle S1 prime, O prime and O. This triangle S1, SO, this triangle and this triangle, the lower one triangle. So we can easily see that these two triangles are the similar triangles, and hence we use the similarity property. These two will be the similar triangles, and hence we use their property that S1S, that is S1S divide by S1 prime O prime, S1 prime O prime. This will be equal to SO divide by O prime. So we use the property of the similar triangles. So these angles are same. These are the vertically opposite angles. This is the 90 degree, and the third angle will also be the same. So we use the property of the similar triangles, and we get S1S divide by S1 prime O prime, that is the lengths that are opposite to the same angles. These are the same angles, and the length which is opposite to this angle is S1S, and the length which is opposite to this angle is S1 prime O prime. So their proportionality will be equal to SO, which is the length which is opposite to this angle, and this angle is same as that of this angle. So the length which is opposite to this angle is O prime. So we get this proportionality will be equal to SO divided by O prime. So SO is given by, or we can say S1S is given by D by 2. So this will be D by 2 divided by S1 prime O prime. So S1 prime O prime will be given by D1 by 2. So this will be equal to SO. SO is given by U, and O prime is given by V. So we get D is equal to, or D by D1 is equal to U by V. So this is the first equation that we have got over here. Now we use the second figure. So in this figure, we place the lens L2 at a position, we place the convex lens at a position L2 such that we get a diminished image of the two sources, such that this lens, the distance of the lens from the sources is now V. Now this distance is V. So the distance which was between the lens and the screen, now same distance we have made between the lens and the sources, and the other distance will be equal to U. So a diminished image is obtained, and the distance between the two images is found, and let's say that is D2. So D2 can be easily found, and D1 can also be easily found. So what cannot be found directly is D, and we want to calculate the value of D. So from here also we use the property of the similar triangles, and we get, from here also we will get S1S divided by S1 double prime O prime, S1 double prime O prime. This will be equal to SO divided by O prime. So here also we have used the same property of the similar triangles. So we get from here is S1S is D by 2, S1 double prime O prime, this is given by D2 by 2. This will be equal to SO is now V, and O prime is now U. So we get D is equal to, D by D2 is equal to V by U. So we have obtained two equations, 1 and 2. One equation we have obtained from figure 1, and second equation we have obtained from figure 2. Now we multiply these two equations, that is we multiply left hand side with left hand side and right hand side with the right hand side. So right hand side when we will multiply, that is u by v into v by u, so that will be equal to 1. So left hand side will be equal to d by d1 into d by d2. This will be equal to 1. So we have multiplied the two equations. From here we will get d square will be equal to d1 into d2, which implies d is equal to under root of d1 into d2. So we know that d1 can be easily found using the eyepiece or the micrometer which is placed across the screen, and d2 can also be measured in the same manner. So we find d1, we find d2, we multiply the both lengths and then we take the under root. So we get the value of small d, and this small d then we put in the formula of the fringe width, and then we calculate the fringe width in case of the Fresnel's biprism. So in Young's double slit experiment, we didn't have to use this whole method of displacement method because there we had slits which were real. So we had slits and lengths could be found easily. But in the case of Fresnel's biprism, we get the two coherent sources, but these sources are virtual, and hence we use another method, that is the displacement method, to find the distance between these two sources. And in this method we use a convex lens. First of all, we place the convex lens near to the biprism such that this distance is u and the distance from the screen is v. Then we find in the first figure, we find the distance d1, that is the images of the virtual sources which is obtained on the screen. So d1 is found in this manner, and then we place this convex lens, same convex lens, at another position away from the biprism such that now this distance is given by v, which was earlier the distance from the screen, and the distance of the screen is given by u, which was earlier the distance from the sources. So in this case we obtain the distance between the two diminished images. So two diminished images are formed on the screen, and distance between these two can be easily found using the micrometer. Then we multiply d1 into d2 and then we take its under root. So that will give you the value of distance between the two virtual sources in case of Fresnel's biprism. So this is how the Fresnel he calculated the fringe width. So in the next lectures we will be again looking at the other experiments that depend upon the principle of division of wavefronts.